Sure.
When we're talking about models, make sure that we explicitly say this is a model we are using, so explicitly saying we are using a model, and make sure we understand the conceptions that students might have. So like the misconceptions, right? Is that what we meant? Yeah. But I don't know if this sentence, this isn't the same sentence. So understanding the concepts before pupils, I don't think that's not what we meant.
In addition to that, I'd like just to add, if we need to change something, we need to do this in a group.
Yeah,
Because we're doing in a
than,
group,
like,
and you need to tell us about it, because
Yeah.
it's not fair.
Exactly,
Okay?
'cause we
You
li-
changed my part without asking permission for it. So please don't do that, okay? I didn't ask you that too. We need to decide in a group.
and we only noticed because Adam opened it this morning, so we've seen, but this isn't what we meant at
Yeah.
all, like, by the discussion. So we meant, we have to say when we're using a model, like tell the students, we're going to use a model now, and then we have to understand the misconceptions that they have about that model. Yeah. But I'm avoiding using the word misconception because we talked about that leads to like an inequality of power in the classroom. So it's their conception of what that model means. We have to understand what their idea about that model is. Does that make sense?
Yes, I meant someone told that you would understand things before pupils.
Yeah, but that kind of is. I think we all accept that as a baseline. Hey, not too bad. We're just discussing our.
You're the first one.
Yeah.
Okay.
I think we could have had this discussion during the discussion.
Yeah, that
So
would
that
have
we can
helped.
decide this and then we can do another thing, and not
Yeah.
changing that during the night.
Yeah.
Or you can just type it to the chat that you want to change
Yeah,
something.
exactly. If you think about it afterwards, because sometimes we all do.
Yeah, something
We
that
could say,
Yeah.
I want to add this, or but it would be nice to know.
Mostly and it comes to talk about other people's parts.
So I don't know what we can do about this now.
I think we should let it the way it is because we don't have time for changing that now. But
I don't know if I change it, it will change the one that he's got.
yeah,
'cause I
yeah,
don't
that's
know if
another
it's-
question. Yeah.
So maybe if I just can I just copy this sentence? Is
For
that-
me, it's fine.
Let's see what happens.
Yes, I think it's important if you're going to change something to let us know. What I also think is the first time that it's fine.
Yeah. I think it's gonna be easy and it shouldn't be crazy.
Because there's just too much text, too many rows.
Yeah, but we need to decide this in a group. You cannot just make a decision for us.
For me, I would make, because
But
it's
you,
my part.
changed my part.
No, it's
Come
also
on.
part.
It,
It's your part.
you want me to show you the previous version?
I don't have the history. Do you have the history?
You just need to
Yeah.
yeah.
That will get rid of the last thing I did.
Yeah, just
The last slide about the what's working, you changed my part. Please, let's not discuss this. Okay?
Can you point me? Is it this
here's
one?
the yesterday.
Yeah, so this sentence was exactly okay. And then which bit?
No, you can leave the way it is. You can leave the way it is now. But you see that there is a change here, right? We feel a great group community. That's what I was supposed to stress.
Yeah.
And not just like the way it is now. But it's okay. I can say it. I can
Yes,
say
you
it.
can say.
Yeah, I can say it. It's fine.
I
It's
think
fine.
maybe when I speak, I change it.
Yeah, sure.
It's not
Oh, I see. Yeah. I see.
Go.
Okay.
Thank you.
I think I
Sleepy.
Okay.
Yes, we're going to go on out of support. Yeah.
We haven't chosen an experiment, so we can invite that they choose a trainer and we go and find one. So we haven't chosen
Good morning. How are you doing? I'm not sure if you noticed, but we are at the end of the first week. And we have a full day ahead of us. It's going to be one of the longest days of HST. You will be exhausted. Some of you will look at us in the evening and be like, I need a weekend. I can already promise you that. But of course, we try to give you as much as possible, obviously. Today in the morning we will start this next round of study group report outs. Thank you so much again for filling all of it in. I've seen some study groups. I'm not using the slides as complete as others, let's put it this way. So I can only encourage you, especially for the individual slides, this is really a way for you to reflect on the program. And I've seen a couple of study groups are not filling anything in there. I'm not, you're all grown-ups, you have to decide how you want to progress, but of course, I would only invite you to use this because it really forces you to reflect on how to get stuff that we discuss here into your classroom. But you are all grown-ups, so you have to decide how you do it. I'm very excited. Again, we have already noted down a couple of points for the feedback, and I will address some of them, or all of them actually today, at the halfway point. But of course, I'm curious to hear them from those 3 study groups. And of course, the three study groups that we'll present today is number 9, number 3, and number 1, which automatically defines who our last 3 study groups will be next week. And having started so brilliantly yesterday, we will then continue today, but of course that only means the pressure is on.
I have a question. When will we prepare a study group session on Monday? For Monday? Because it's Monday morning, right?
No. The next one is only
Oh, it's
on,
Wednesday.
Wednesday.
Sorry.
So we have the study group session number 3
Oh,
on
we have
Tuesday.
time.
It's all
Okay, I thought it was
the,
on
the
Monday.
fact that you assume that it's not carefully planned out hurts me. All right. And of course, before we start, yesterday I hope, well, not only I hope, I know, and I have to prove because I've seen all your feedback slides. Yesterday, exactly the one thing happened that I was hoping for. I lost at least half of you, if not even more. I really pushed you into agony, and I really wanted to have that. I mean, I'm not trying to sugarcoat the session. It's exactly what I want to have, and that's also why Frederick will come back today in the morning and we'll streamline it a little bit more. But I really wanted to see I wanted you to see 2 things. Number 1, what I discussed earlier yesterday, what is a particle, is really a tough question for us as scientists, but that makes it even more difficult for you because you have to answer to your students. So I hope that you've seen this, number 1. And number 2, I hope you've experienced how sometimes your students might feel in your classroom. You're like, are you all with me? This is clear, right? 1 second pause, nobody objects. Okay, let's continue. Never do that. Never do that. So I hope you've seen that, and of course Frederick will come back today, and it will all start making a little bit more sense. I'm not promising too much. And then of course Dave Barney will come, and he will talk about his experiment. He has been with CMS for a long time, and you will fall in love with Dave the moment he starts talking. And this is going to be a fantastic introduction to our visit then to CMS, which is going to be big and messy. It's a 2-hour full slot. Milena will be with you. She has the hardest job today. She will have to keep the time, and it's going to be difficult because you will all be split into 4 groups with 4 guides, and they all have their own itinerary, and none of them is keeping the time, so it's going to be a nightmare. But eventually all of you will get a chance to wear a proper helmet, go 100 meters underground. You will not be able to touch the detector. It's running. It's very unhealthy to touch it, but you will be very close to it. And yes, you will all get to take a very nice selfie, a nice Facebook profile picture today in the afternoon with a nice helmet and everything. And then the bus will bring you back. I will come to you in in 1 second. The bus will bring you back, and of course, depending on how late we are, this coffee break might only be a buffer. But as a function of when you come back, you will then decide when to start. So Milena will announce that when you come back, it's all going to be taken care of. And then we have our fantastic movie night tonight. Tonight is movie night, where we watch Particle Fever in the main auditorium. I can already promise you there will be chills over your skin, because the moment they announce it and you realize I'm sitting in this room, it was my idea. I at least always get chills, but it's let's see. Yashka, please.
So flat closed shoes for the visit?
I will announce it before the lunch break, but absolutely yes, today is the closest and flattest shoes that we have.
Do we need a computer for Milena?
Absolutely, yes, I will also announce that. When you come back, you see the bus will bring you directly to the CERN Hotel, and absolutely yes, then you have a break. As a function of your return time, you will see how long the break is. But then when we start again in the main auditorium for this, you definitely should, or no, you have to bring it up to make our life easier. All right, and Francisco.
Yeah, that's me.
The birthday party
I take some candies we can share, but please be careful to split it on the floor. Or
Very nice. I love this tradition. I'm curious to see what the others think. I'm glad I was first. I was about to say, are you okay? There's no picture. What's that ready?
Guys, I'm gonna do the picture real fast. I'm sorry.
Are we running the picture? Whoa!
For 2 seconds.
Wow, so rude.
Birthday quote. Sorry.
Sorry, can you stop for 2 seconds? Okay, 1, 2, 3. There you go. So
Nice. Yeah, I wasn't sure if if everything is okay because I was looking at you and you were not saying big.
Yeah, no, it's like waking up. So it's gonna take like a couple of
All right. Everything else we will discuss, especially for the weekend. There are plenty of things to discuss. I've already seen in the group chat a couple of ideas bounced around. We will all discuss that then at the video and outlook. Okay. Philip?
One last thing. If you any of you have time during the coffee break, all of you who haven't signed the guitar yet, please come to me or I'll try to find you. Also,
for sure.
And I would also ask our lecturers to sign them as well. Louis already did yesterday. I called him before he left today in the morning.
Awesome.
And we'll see if we can get everyone.
I think this is going to be the most precious guitar of all your collection. All right.
Already is.
But now, of course, it is time, and we are running a little bit behind schedule. But since I asked study groups anyway to only present for 5 minutes, we will see today how it's going. So, without any further ado, study group number 9, please.
Everyone just go under
Pictures, yes, they match up. Very nice. All right, your time is running. Let's go.
Once upon a time, the ninth planet from the sun was Pluto, and therefore we named our ninth group Pluto. A couple of years before Pluto was cancelled as a planet, I managed to win 7 tennis competitions at the recreational level here in Switzerland, using tennis balls like particles as an accelerator.
Nice.
And it turned out that I behave like an anti-tau and neutrino. What about you guys?
Okay. So I'm Adam, and I'm from Czech Republic, and I'm obsessed by radioactivity. So I bring everywhere my Geiger counter, and I have an amazing collection of radioactive items. So if somebody needs uranium, just call me. I have like kilograms of uranium, like really.
This is the moment where we see Adam moving a little bit to the side now. Okay, very good.
Okay, I'm Lucas, I'm from Brazil, and nothing very special and funny to share with you, and then I remember that I slept in a hammock for 10 years, like, not for 10 years, like, until I was 10 years old.
Hi everyone, I'm Claudia, I'm from Guatemala, and I love snorkeling. In fact, one of my favorite memories, and you could close your eyes, but just imagine being in the middle of the Atlantic, and then just seeing a beautiful sea line going up in the middle of the sun and the sea mountains. And I'm also the technical and survival advisor of my team.
Hi, I'm Virginia. I represent Switzerland. But basically, I am Italian. I moved here 20 years ago, and I work here as a teacher of physics. What is always strange for me is that I really hated physics when I was a teenager. So when I start my course with my students, see me the first time, I say, if you don't like it, I don't understand. But it's not impossible. I do. And I'm here.
Hello, my name is Jenny. I'm from the UK. My fun fact was I once swam 10 kilometers. I got t-shirt to prove it. And in September, I'm going to try and do it again. So key takeaways, one thing we've been talking about in pretty much all of our group sessions is the use of words, and like Louis talks about it a lot, like how important words are and how even experimental and theoretical physicists using these words, particle and field, and they don't even know what they mean. So we kind of find that quite mind-blowing. And career pathways there are at CERN, which we didn't really appreciate before we got here.
No, it was
This is not our slide.
No,
I mean, it is our
no,
slide,
it
but
is,
not.
but it was the one of the.
Oh, sorry.
Oh,
I screwed
sorry.
up.
Yeah.
I just.
Did I screw up?
We need to go.
Oh yeah, I screwed up.
Like yesterday.
Oh Jesus Christ, this is the last.
Sorry.
Last is.
Let's try again.
Nobody.
See, language, we still talked about it, it's fine.
Sorry, I thought.
I don't have to say that again, but.
My point is understand the Higgs field, and we are happy to announce that we understood it all. No, but of course, I think a part of our conversation is, and the reason why we're all here is just to try to understand how it works. And of course, I'm not going to go over all of the questions that I have in my mind because we can probably all now give a definition at least from the textbook of what it is. But then it's like, so if it's static, how does the interaction happen? And is it like more like gas or is it like molasses? Is it, not all the questions, but I think for us, one of the key takeaways was we don't understand the Higgs field yet.
Okay, it's coming. Please accelerate, you're running out of time.
All right, another takeaway is that we need to stress out that when we explain particle physics using a model or models, we need to stress out that we deal with model, not with real life. And we had different points of view whether to use a contemporary model at all the levels or not. Anyway, it would be a good practice to go through historical models so that people can see how science developed.
And I think that one of the most interesting takeaways is the realization that this place was built by engineers, not really the scientists or physicists, but really engineers which must overcome the problems and obstacles to build everything and to get everything maintained.
And we all realize our problem solving is important. There are still problems that we as humans think but so let's our focus on
All right.
and that's it.
Absolutely.
Okay, highlights. So we've had so many amazing discussions. Even before Frederick, we had loads of discussions about reality. Some of those were helped by lubrication. I'm glad that we did tonight because he would lubricate himself to help him discuss reality a little bit more. So it should be good. Should be good.
Good. So we are also every day is much more in fact. And also to be here as a
Well, about what it's working, I think it's a general perception that we are in a very great group community. So all the conversations we have had in our group and with you people, it's been really nice. So we definitely find that it's really working well.
Sorry. Just this is feedback for improvement. Just for every speaker that we have. This is 37 countries represented. So just I know you probably do, but an extra reminder about using colloquialisms and like Harry Potter example, like or somebody said something about my guy rating the tools that we were using. So I think I think it's always good to think about those things when we're teaching, not only for us but for our students too.
Yeah, and some improvement was about the cloud chamber, because we spent a lot of time to build like the large one. Every part was special made in CERN, but on the last time, like in a few minutes, it was option to build it like from the scratch, from DIY thing, which we really do with our students, but we didn't really try it like our own. So I think it would be much beneficial to build a DIY cloud chamber.
Not within 1 hour procedure.
Okay. And as we only have a few weeks here
year, not 2 years. And then it would be very nice if we could maximize the time on how to deliver this information to pupils and minimize the time about describing individual history and irrelevant, complicated explanation.
An amazing thing. Every time we had a study group, we measure radiation background, and no worries, it's safe here.
Thank you very much, study group number 9. Let's move on. Number 3.
Thank you.
I can only encourage every group to keep in mind you have 5 minutes. So far, every study group did not mention.
Alright, so our study group name is Harondi Sam after 333, like Magnus, in 3 of our languages. We left English out. Okay.
I'm Joe. It's not very fun, I think, but I have broken my back on 2 separate occasions. Wow. Not fun.
Yeah. Happy that we
It's such a physics reason to why. Tell them hammer.
Golfing.
Like seriously?
No, I wish
Put a line.
Let's give him the puppies out of a good building.
Okay.
Okay, hi everyone, I'm Noor, I'm from Pakistan, and the fun fact that I've written over here is kind of a dark comedy. But this is something which has stayed with me from the last time I have any memories of my life. So it's that I want to get slim, but I really love to eat. I didn't really have any pictures of myself, but I figured this was the right audience. My name is Amanda from Newfoundland, Canada. This is my high school physics teacher, and he, along with some of his colleagues and members of the university, nominated me for the award that got me here. So I figured it was great to And it's fun fact, I have square feet, which plagues me for shoe shopping.
Hi everyone, I'm Sovic Pradhan from Bhutan. I'm not sure whether it's fun, but one of the facts is that while teaching to my students, I like connecting the spirituality and the astrophysics, because Bhutan being focusing more on the spirituality aspect, so when I teach to a student, student gets more excited. And one more thing that I would like to add on is that I think the fact is that I'm the first one representing Bhutan. And that
Hello, I am Karol from Hungary, and as I guess, I am the oldest man in this auditorium. I am not happy for it, but I had time enough to study physics and computer sciences, and this is the second time I am here in the SEN, and I hope you will do the same.
He showed us the picture from 20 years ago yesterday of him here 20 years ago. Adorable. Yeah.
Alright, now I will try to find the correct slide.
Yeah, let's choose the yes, here we are. Is that correct?
Yes, color code. Yes. They're right here. Yes. So, after was this the garbage? Yes. Oh, it's funny. Milena liked it. So students interact with matter differently than we do. Honestly, everything interacts with matter differently in terms of considering, and I think Frederick's talks yesterday kind of put us in the seat of the student, and in terms of, you know, taking off our teacher hat for a moment and putting on our student hat and being like glazed over look for a moment. So it was kind of very appreciated. I actually love that. But in terms of trying to always be aware of our students' perspective.
I think one of the main themes across both conversations we had or lectures we had yesterday was that all models have advantages and also shortcomings. And considering those when we're choosing them and also discussing those when we use them is important. And that does not only include just like the graphical or visual representations of phenomena, but also in some cases our mathematical models of phenomena.
I think we cannot fit everything in our curriculum, but I can fit everything that's why I am very excited to be in the sites and see how where is the engineering which is done here in science. This I can take with me and my enthusiasm. Together with here, I can show to my students.
Before I came here, I assumed that CERN was open, so everything was available to the public and it was collaborative out of the good nature of science. But now that I've been here, it's not only that, it's also because the scope of CERN is just so wide and large in terms of price, resources, and manpower that it's actually necessary for the survival of the project.
Yeah. I'd like to include the 2 points. It was so the passion. We found that the passion out here, the people walking out here, and they had that dedication to know about the universe, how we came into being, and the motivation needed. And that's what we, as a teacher, we try to inculcate the intrinsic motivation for the students to study and, in a way, help them to, go for their, ambition, to achieve their ambition. And another thing that we came to know from the various lectures is that we are still far from the truth. It's still difficult to get the real truth, but that's the beauty of it. That's what keeps us going on, and that's what keeps the scientists move forward to get motivated and to know about the real truth.
Okay, during the past few days, we have seen that the science and engineering that went into making and running LHC is like so advanced, complex, it's interdisciplinary, it's collaborative, it's so many things which are impossible, but we have seen that, it has a successful outcome. So it means, impossible is just a state of mind. We just need to push ourselves towards the boundaries, and hard work can actually make anything possible. This is one of our main takeaways from this program.
I was learning a lot yesterday, and I want to mention the Jeff's lecture. Then I realized how important it is to be careful how to select the words for each sentences, and like particle system or decay or transformation. That's quite interesting.
Presumably as teachers, we're all really planners, organizers, set it all out. We've had all of our lectures have been fantastic, but we've seen very different styles of lectures. And the irony, or I guess the takeaway from Frederick's lecture yesterday, is that randomness and chaos that you cannot control and have to accept. And I think that's something, even for me personally, having to accept that no matter how well your plans are or how much you think you have everything ready, that there's always something that will be thrown at you from a student, a parent, from the universe, whatever, and that chaos is real and is out of our control. So having that mindset of having a plan but being able to still roll with it is something that I took away as a big learning from yesterday.
One of the things we learned from this lecture is, while it's important to show that we have a variety of models and that models can change over time, like we don't want students to think that what we show them will be what science will be forever. It's wise to show the most correct model that we have first, and then go back in history to show them how it's changed.
And we also learned that the answer to the question, what is a particle, should be like audience dependent. Because it is a complex concept, so we should, keep ourselves limited to the level of our students, and let's not, we should not cramp up their minds with a lot of information at the wrong time.
Okay, let's go to the next slide and finish it up, please. Terrible lot of time as well.
I think for me the visits to the site it is very important. That's why I am here, because every information you can get from the internet otherwise, but that close looking to the systems and to talk with the engineers and the local scientists is very helpful for me.
Brian main quality of lectures has already been mentioned. Awesome, astounding, all the different types of lectures, different personalities that came through, top notch.
Yeah. And with that, we would like to thank Jeff and the team for your outstanding commitment and for this top-notch organization of this program. We are loving it, and again, we still have 1 week.
Exactly. You can still score it.
Okay. And the last point is exactly what I mentioned a little while ago. The level of the lectures should be audience dependent, but I've got a very special comment for the audience as well. Like there was a time in the lecture yesterday when I was on the verge of background in quantum field theory, but then what kept me back from it was the fact where are those people themselves, right? So please speak up.
Yes,
This is what we should as teachers.
Any questions?
No.
Everyone okay with this topic? All right, let's do it. This is all of us yesterday, or half of us, or 3/4 of us.
And our takeaway from it as teachers should be that we should maybe stop for a little more time, look at the audience, ask them clearly, and then maybe move forward. Because it happens with us most of the times. We say, okay, is it clear? And everybody's like quiet, and we're like, okay, let's move forward.
Yeah.
Yeah.
Biggest learning ever. Thank you. And we are running a little bit behind, but we'll still have study group number 1 please on the stage. And I assume someone left glasses here? Is someone missing glasses?
Joe Dice.
Claudia is going for the
Yes. Okay. I'll put a 5 in one, and then I'll tell us the 5. I told you, I was Swiss in a previous life.
All right, let's go.
Okay, go.
Okay. Hi, so my and my career college changes every 6 months. Next college change due September 2nd.
I'm Sue from Australia. I've had about 4,000 jobs in my lifetime, and one of them was I was a wedding florist, and I had my own business, and I did flowers for weddings.
I'm Adam from Ethiopia. I love growing mushrooms, if you want to know. Of course, it is. I'm the first Ethiopian here at here.
Yay!
Okay, I'm Stéphane from France, and I don't know if it's a fun fact, but I'm president of chess club. If some of you are chess player, I will be happy to play with you.
All right, have fun.
Hi, I'm Shreya. I'm from India, and my nickname is Sangeeta, which means I can sing well. Yes, I am a professional classical vocal singer. But the thing is, it's very difficult to have a career on singing, whether we have like 1.44 billion people in India. So I found physics as a super cool career that I can be a teacher. For me.
I love it. Very good. Okay, this is study group number 1, and let's make sure that Jeff finds the right slide.
40 something.
Yeah, here's Tuesday, exactly here. Thank you. Oh, even with animations. Okay.
I will explain these to you. I'm sorry.
Okay.
Oh, I can do it.
Oh. Yeah, this is our first takeaway actually. We're really surprised that we saw many collaborations here at CERN to make everything success. There are researchers, there are scientists, teachers, and everyone is here working for this big organization to be success for everyone. So this is our main takeaway, including some of the projects which are very important for future.
So I really take away the whole point of visualizations and models in our classroom. So I made a worksheet, if anyone wants it, yesterday about designing a simple particle accelerator. If we have time, I can share it, but I'm not going to share it. But one of my jobs was working in an engineering firm, building trains, so I understand the idea of problem solving an engineer, so I really love giving students like short, sharp time frame. You've got 10 minutes, you've got this equipment, go and build a particle accelerator. So I made a little activity, if you guys want to do that, I did yesterday with the help of AI. And a whole bunch of online simulations, so I'm all about providing resources, so these are just some that I found.
Okay. The next topic is about engineering, and the lecture given by Ray.
lecture, I thought that engineering was a little bit boring. For example, in my high school, there is this topic called science of engineering. And when I see how works my colleague, it's close to do it yourself and really science. But I changed my mind after this presentation. And I would like to, sentence which resumes how he built the tube in the detector. He said nothing contained by nothing. I love this sentence. And it makes sense with our job, which is build knowledge from sometimes nothing.
Yeah, so I found it, so make classroom as joyful as possible. So I'm learning from Jeff again, and I try to implement in my classroom. So it is not practical for me to implement everything in the classroom. We have a large classroom with 90 students. So it's very difficult for us in India, like implementing or doing anything in engineering. So it's better, and we have already, we have a overwhelming syllabus. So I like to make the classroom as joyful as possible. And so I have a short note for you. Do you know what a boson is? Of course you all know. You are all physicists. So boson is the particle with integer spin. But you know where the name came from? Yeah, so Tendrona Bose. So I am from his place. So I am from West Bengal, India. I am very proud to say you that. And I am from the place where the birthplace of Shotendranath Bose, and Paul Dirac named after him the particle boson. And I found it like very interesting for you. And we used to organize seminars on his life and lectures and his career for the students. So I found it sometimes better to do some seminars. Yes, it's very difficult doing something else from your curriculum. So it's very difficult for getting permissions, but I always try to connect with them. We have a Bongyo Bigyan Parishad there, and we try to organize seminars as more as possible on his life and lectures and his works, and also try to interact with students as much as possible in like this. And what he wrote, like in Bengali, যারা বলেন বাংলায় বিজ্ঞান চর্চা সম্ভব নয়, তারা হয় বাংলা জানেন না অথবা বিজ্ঞান বোঝেন না. So we try to interact with our students in our mother tongue, which means who are saying that it is not possible to communicate with the students in your mother tongue about science. Either they don't understand the mother tongue or they don't understand science. So we are trying to communicate with our students using our mother tongue. Yeah.
What's working and the highlights? I mean, I think, can everyone read? Do we want to read it out? Sorry, I don't want to repeat what everyone else is saying. Stefan had a very important improvement. Stefan,
yes, it's for Jeff. Sure. The next time, could you shut down the LHC?
I will call them right now.
It's easy. The button close to the button, proton.
Yeah. Actually, we can talk to Frederick. I mean, he's in charge. Move the column a little bit closer. Okay.
And just really quickly, sorry, this joke. Engineers can't win a Nobel Prize, can't get laid. Physicists, they're mock engineers and they can't get laid. Mathematicians are mock engineers and they can't win a Nobel Prize. But all of them together are better than chemists.
Thank you very much. Moving on. Very well done.
Sorry, rush through that. So
thank you. You can see Sue was really a project manager with pushing them and watch like we are running out of time. Very good. Thank you very, very much for all your feedback. Of course, now for the remaining 3 study groups, you not only see where this is going, but you can definitely show to the other 6 study groups how to keep time, because so far no study group managed to present 2 slides in 5 minutes. So this is going to be your challenge first for next week. But I want to just remind every study group that on Friday, when you have your final reports, first of all, we will be in this very room, so you can already envisage yourself. It will all be switched on, everything will be on recording, you know. And this is where you can present them, so also to make it interesting, what you want to act out, I don't know. But you will still only have 10 minutes for your presentation. This is about the same time that every study group has taken so far, for 2 slides only. So you really better prepare what you present so that we don't run behind. because the recording team from CERN will not be happy if every session runs half an hour, because also we will then only finish at 6 o'clock. Okay? So, and having said all of that, and of course the feedback was very similar across the study groups, so we will definitely take that forward, but that's why I will now invite Frederick to the stage again. Good morning. And this time, we will start with some slides first.
Yeah. So he was complaining about slides in 5 minutes, right?
And I mean, yeah, we have goals, right?
Go back, we didn't see those yesterday. Go back.
So here, if we start maybe here and go at least 3 more slides forward within the next 10 minutes, I think that would be awesome. Thank you very much. I think it's fair to say that your first lecture yesterday triggered nice discussions. And I think
we loved it. We
loved it. I'm not negative. I'm just saying you prepared a nice second lecture now, or we are prepared to have a second part that we can. So my goal for sure is, because that was something that some people feedback directly to me, Feynman diagrams, what those lines actually represent. So what is it that you've drawn yesterday, and how do we use them? So I think this is something that we can do in the next 3 slides. And then of course it's really going to be up to you to ask the questions that you want to have the answers to. If that's okay with you? Thank you very much for being with us. And yes, we are a little bit behind schedule, so I will shut up the stage, and the teachers are all yours. They're going to present it.
Yeah, so I also got feedback from some of you that they were completely lost yesterday. So while I always like to confuse people a bit, of course the goal is not to get lost completely. So let's see if we can set some things, we can tie some dots together now. Okay, Feynman diagrams. So yesterday I have a whiteboard here, right? But then we need to move the projector. I touched, I was going to say briefly, but that is not true. Perturbative expansion and how this leads to Feynman diagrams, etc. I guess this is what I lost a lot of you. So let's see if we can reverse the logic a bit. So, this was evident or not? Because actually I never said that yesterday. So, but what we are drawing when we draw a Feynman diagram is some kind of 2D slice of 4D spacetime. Right? You can always assume that we don't take coordinates to literal at that moment. It's anyway a pictorial representation. Remember, it is not literally particle moving here. It's a pictorial representation for a mathematical contribution, but it represents some kind of one direction would be time, one direction would be space, right? Because then people say, oh, they're the same, 4 dimension, and not exactly the same, of course. Time behaves differently in space-time, you know that. You get the sign difference geometric. If you don't know that, just accept it from me. It's not exactly the same thing. It is treated as a 4-dimensional thing, but not every dimension is treated in the same way there. So, especially also because for us anyway, as mere humans, it's not the same thing, right? We experience time in a different way than we experience space. That is also an important thing. So, blah blah blah, perturbative expansion, we will maybe come back to that later then, to see if we can tie those knots, but let's focus on just trying to understand how you build a Feynman diagram, what would it mean pictorially. So as I said here, visual way to calculate elementary processes. Maybe I could rephrase that also as it is just representing one contribution mathematically. And why did Feynman start doing this? Because the formulas get extremely long and difficult to write out, while the meaning is not that difficult. Like the one I showed yesterday with all the phi's and the phi x and phi 1, already that one was only a first order diagram. And if you would really write it out, you have to write coordinates everywhere, you have these integrals, you have to put the quantum states, it becomes the full blackboard for one simple first order contribution. You can imagine it explodes the moment you go to a few second order contribution, and you just write papers of papers. While, well, first of all, it's not really needed to get the meaning out of it. And secondly, this increases the chance of sign mistakes and kind of things enormously. So Feynman diagrams are bookkeeping. They represent these individual terms in this very long expansion, and so Feynman just found a way to do that diagrammatically. There's nothing more to it. We do that a lot in physics, like when you do group theory, when you do Lie algebras, and you look for different representations. You have these, I forgot what the name, in Dyson diagrams, circles and lines you connect. And again, it has no meaning there. There is even further away from a physical meaning because it's pure mathematics. These are just ways to see what kind of terms do I get. So Feynman diagrams are essentially this. An ironic device to get what would be all the possible terms in my second order expansion. It's easy to draw stuff. And then of course the next step is to make Feynman rules. Let's say, how do I translate this specific diagram to the exact mathematical contribution? Because then it is easier to do your bookkeeping. Then you can just say, let's draw all third order contributions to the electron. Right? Will be quite some. I don't know the number by heart, maybe 24. Probably this is kind of the order. But you can easily draw 24 small diagrams. You're not going to write 50 pages of 24 contributions, right? And then you're going to say, okay, let's translate each and single one of them to their mathematical contribution. It's also an interesting way to work with Feynman diagrams, not only for your own bookkeeping and avoiding mistakes, but also in communication. Why? There was this story about linearization yesterday, about, you know, the charge being infinite and all these kind of things. How the fact of linearization, meaning like, I'm going to say the bare one is infinite, and it converges to finite one. How that enters in your calculation is actually by like cancelling diagrams. You're going to add some extra stuff that represents this effect. There is the other thing that all your integrals, even the simplest one, is divergent. Divergent means infinite, it's not converging. And what we then do is called regularization. We're going to say something like, imagine it's not divergent. It's a standard approach. You say, an easy way is you do an integral from minus infinity to plus infinity of x. This is quite divergent, right? We'll give you x squared, you're going to make this times infinity. So then you say, oh no, actually this thing is the limit of a to infinity from minus a to a. You get a result that has some value, but you know it is infinite, right? But then you're going to postpone that. You're going to keep this limit outside, because in the end we have several diagrams. And you hope that this a somehow cancels between different diagrams. And most of the time it does. And then of course, if you have a minus a plus some other stuff, a minus a is gone, and then you can take the limit a to infinity because there is no a left. Mathematicians would tell you, well, this is like doing infinity minus infinity 0, which is forbidden, which is also true. So, which is why typically mathematicians don't really like quantum field theory. But there is a few that have actually gone through the math in extreme detail and built a mathematically sound quantum field theory model. It exists and it is valid. And this is a bit more lazy and just know it is valid, so we do it.
Regularization is different from normalization?
Yes.
Okay.
Regularization is the first step you need to do to be able to even compute anything. By the way, this infinite thingy, making it a, is the easiest way, which most of the time doesn't really work, because we're not in a one-dimensional integral, in a four-dimensional integral, etc. So what we typically do is actually be like, but this integral is divergent in 4 dimensions. It is not divergent in 3.99 dimensions, which is true. Most divergences are in integer dimensions. And so then we say, oh, imagine that actually we are having our system, our quantum field theory, in 4 minus 2 epsilon dimensions, with the limit of epsilon to 0, right, with the same cheat tag. And then you get a whole different way of dependencies in epsilon. You get typically 1 over epsilons all around. Most of them cancel, some don't. And those you need to renormalize. But that, coming back to Feynman diagrams, that is why those Feynman diagrams are so interesting, because you can really like collect them. These are finite diagrams, meaning we know that if we, not finite, not infinite, we know that if we combine them, the infinities disappear. So, and this is the crucial, let's say, breaking This is the one that needs to be renormalized. It would be very complicated to communicate that with 50 pages of calculations. And by the way, page 37, second paragraph, is the breaking. You see what I mean? Feynman diagrams is bookkeeping, it's communication, it's understanding. Okay, no essential meaning. I convinced you of that. The mistake goes in people believing this what happens, but I hope yesterday I convinced you on the fact that this free electron that you actually draw does not really exist. So, an easy visual way to calculate elementary process is the essence of what they mean. Then, we said expansions, orders. You can, in one go, see what is the order of a diagram, meaning what step in the expansion you are calculating. Because, if you remember, and we will come back to it in more detail, there was this expansion of the exponential, blah, blah, blah. So if you go to the second order, you get more fields. So you're counting fields. Right? Am I losing you here? No? Okay. So, remember that in this exponential, quadratic fields were the free theory. And the moment you have higher orders, 3 or more fields, you go to the interaction theory. 3 or more fields are all in the same coordinates, so that represents a vertex. As I also zoomed in slightly. So one vertex corresponds to one order of your expansion. You with me? Very good. So we're counting vertices. So if you see 3 vertices, this comes from the third order term in the exponent. Now in practice, because I told you first order is always 0, etc., we count them evenly. So the order of a diagram, the first diagram that can exist, that is not a trivial one, is the first order expansion, it's the second order exponential. So every 2 vertices, we have an order of the diagram.
What's the vertex?
Vertices means a point where different lines meet.
Yes,
It means an interaction. It means we have more than 2 fields in the same coordinates, or they're doing something to each other. I mean, again, you can think of this as 4D spacetime, right? So all 4 or 3, 4 fields have the same coordinate, so they all enter and are gone, or 1 enters and 2 go out, or 2 enter and 1 goes, etc. So that all means the same thing. That's yes.
Just to make sure that I got it. One vertex means one interaction between how many fields?
At least 3, because you cannot have a vertex with 2 lines, of course. Then it's just
Yeah.
3, 4, and then the moment you have 5, or standard field theory breaks down, because you can show that it's no longer renormalizable. You get issues with your dimension. Remember thinking about dimensions yesterday? Your dimensions go they go to hell the moment you have more than 4 fields. However, nobody forbids you to make a theory that is not renormalizable.
Okay.
So the renormalization, this charge infinite is actually finite. This thing is very, very tightly tied to the dimension of quantities, which comes from this regularization by dimensions. And so, that is very stupid. Dimension here means units. Important. When we say the dimension of something, we mean the units. The dimension of speed is meter per second. So length per time is the dimension of speed. It's not space-time dimension. But so, having non-integer space-time dimensions will change the dimensions of objects. It scales wrong, and that you need to renormalize and correct. So these are very uniquely timed. If you want your theory to work, in other words, that renormalization will not go in all directions, but actually works, you cannot have more than 4 fields. A lot of people, especially in string theory, will have more fields, and then they just say, I assume that somebody else made a theory that is like more general, that is renormalizable, and this is some kind of emergent local effect. Did that answer the question?
Yeah, but
and then it's yours.
I think before, like when you say these fields, you're not saying like electric fields. You're saying like the field.
Quantum fields.
The quantum field of the electron or the.
Yeah, so particles, if you want. The mathematical things that describe.
Okay, and another thing that I got in mind yesterday was when you say like these fields, are you saying like the DFC of like a field is a interpretation of the DFC?
You mean C particles?
No, I mean like all spaces are full with virtual electrons, absence of an electron in this infinite electron field is a particle. Do you want? No.
Directly is not used anymore for quantum.
Okay, that's what
Yeah, so there is like, historically you come to this theory in 20 to 30 different ways.
Okay.
So it can get very, very confusing in nomenclature. I have not really heard that in the term Dirac-C. And it doesn't mean it's wrong, right? It just means that I don't know what it represents. Also, like, mathematics never changes. The theory we made 60 years ago is still the one today, but we polished it, etc. It's still mathematics. But how they would explain it, it would change a lot. Nobody today would say, oh, when a particle goes very fast, it gains a lot of mass. That's what they said in the 80s for relativistic effects. Today, it's convention. Today we prefer saying, no, mass is a constant thing, constant property of a particle, rest mass if you want. And what it gains, well, it's energy, a gamma. And we would write E is gamma mc squared. Always true. If you write E mc squared always true, then mass is not constant because it absorbs the gamma. It's a matter of interpretation, convention, and it also matters a lot that you know who you're talking to. Because, for example, older people will tend to use mass still as a non-constant. And if this is not explicit, that you might be discussing for half an hour, 1 hour, until you realize, you don't mean mass, relativistic mass, or whatever. You see what I mean? Math never changes how you communicate, how you. And so I'm not sure what you mean with the Dirac-C.
No, that's okay. I think I got it. Thank you.
Okay, sorry.
No, that's good.
Okay, so you say that theory is not generalizable if I have more than 4 fields.
Yes.
More than 4 fields in one vector.
Yes.
So if I have 5 fields, no more than generalizable.
Exactly. So you can have an electron going in a vertex, and out of the vertex you have an electron and a photon. So just electron radiated photon. You can have electron going, it will be positron, but fine, have a symmetry that flips antiparticles with time, etc. So electron positive going in, photon going out. You can have electron positron going in with the photon going in, nothing going out. All these things work. You cannot have, okay, wait, bad example. Because you cannot have electron, photon, but for other things, bad example. Well, you have gluons. Gluons have 4 interactions. There are very few particles actually that have 4 interactions. Gluon is an example. You can have 1 gluon radiating another gluon. You can have 1 gluon radiating 2 gluons, or 4 gluons meeting on electricity. 5 gluons, no. Can never happen. Of course, it can. You just zoom in, right? You can have 4 gluons or 3 gluons joining into one, and a bit later this one's splitting in 2. It is a very short time frame. You zoom slightly out, it looks like a fragment interaction.
I cannot have 5 gluons.
Exactly, and this is what I mean. Like, you can make non-randomizable theories at a certain scale. I could zoom out slightly, not even much. Maybe it's a very, very small time frame that this gluon, the 3 gluons became 1, go to 2 again. If you zoom out, it looks like 1 point. These are local theories. Perfectly fine, but if it's not renormalizable, it can never be everything. That is the difference. So people work with renormalizing theories a lot in supergravity and in string theories, etc. But it is assuming there's another theory behind and we are doing some local things. Does that answer the question?
Yeah, please.
Okay.
Excuse me, I have a very low-level question.
No worries.
I wrote three fields mean vertex, and that means interaction.
Yes.
Is a field related to only one particle?
A field is always corresponding to one particle.
Okay. And well, when we know, for example, the Underglass theory, I was told that collision between 3 particles was extremely rare.
Which theory? I'm sorry, I hear you very
The
badly.
ideal gas theory, for
Yes.
example, when we
Yes.
show our students that we have some collisions between 2 particles, but it was extremely rare to have 3
Sure.
particles meeting, or in chemistry too, for example,
Yes.
when we want to explain mechanism. It's
I can answer that in 2 ways.
sorry?
I can answer that in 2 ways.
I would like this.
Way 1 is, well, ideal gas theory is macroscopic. It's classic. It's classical dynamics. This is quantum. Remember, This does not represent reality. If I draw a vertex with three fields, it does not mean I have a collision with three particles. It is just a mathematical tool to describe certain orders. So they're not really the same thing. That's one explanation. That's the main explanation. The second one is, well, let's get more intuitive. Fine. Three particle collisions are much rarer. But two particle collisions in this context means one particle just existing. Because a vertex is any coordinate you take. I take any coordinate here, one in, one out, which is just a particle existing. So this is the baseline. So subtract the baseline and you look at whatever is left. The first thing you can see is 3. And maybe it happens very few. It doesn't really matter if it's the only thing you're looking at. Everything is relative, right? If it happens 1 in a million times, it is the only thing you're counting, then that's a lot. You see what I mean? That's the to the first explanation. Okay, that's a lot of questions, but I had promised to go to the next slide.
I just need a quick explanation on dimensions again. Like we have 4 dimensions, space, and time.
Yeah.
Do not have any more dimensions ever in this theory.
I mean, it depends. If you have string theory, you have at least 10,
yeah,
11,
okay.
26 if you're Bolognic theory.
And you were connecting like dimensions as units and dimensions. I
So
didn't
this-
get that here.
Yeah, this is also not that trivial
Okay.
to say in an intuitive way. Let's see if we can come back to that,
Okay.
because then I would need the blackboard to show you.
Okay.
There's a whiteboard.
Yes, but then we remove the projector, etc., and I have made a problem about slides. I guess so. Give me 5 minutes.
He's like, you're trying to get me in trouble here.
So let's keep that in mind, and keep all your questions in mind. We will have time afterwards. So let's go the other way around. Because I started to explain you Feynman diagrams from where they come from, the mathematical basis, which is not trivial. I now realize if you don't have that mathematical background, obviously, which is very advanced math. I did that because I like it, because it really makes you understanding that it is just math. It's no meaning, right? And it also shows you how these things actually merge and how it's actually just, a shortcut to avoid calculations, etc. How you, on the other hand, how you typically get taught is by, boom, these are Feynman diagrams, this means it's an electron, this means it's a gluon, and then you, of course, get all the misconceptions. So let's do that now that you're ready to battle the misconceptions. So representation. Different lines for different particles. Straight lines with an arrow are fermions. Fermions are math. Again, represent a certain contribution of a theoretically non-existing free fermion. But let me not force me to say that every time. So, fermions. If you put time on this scale, and the one space you're looking at in that scale, when the arrow aligns with time, it's a particle. When the arrow is opposite to time, it's an antiparticle. Convention, but you need to keep track of what it means. Because if you're going to reverse time, mathematically, you flip time, the particle changes into an antiparticle. Also an important thing, people see antiparticles as different things. They're a different representation of the same particle. Where it comes from originally is that when Dirac was making his first relativistic quantum theory, the first thing is, typical Dirac equation, he noticed that his solution allowed for negative energy solutions. His formula allowed for negative energy solutions. People don't like negative energy. It feels very counterintuitive. What would it mean, negative energy, etc.? A particle having negative energy. So he chose to, instead, to say it in a very layman way, to move the minus sign to other properties of the particle. So that instead of saying an electron can have positive energy, negative energy, he's saying we have two states, particle and antiparticle, both having positive energy. Right? It's a bit less simple than this, but that's kind of the gist. What I want to give you here is that this is a choice. This is the same as saying rest mass versus relativistic mass. No, mass never changes. It's two options, two choices for the same mass. Why is that important? Because there's no difference between the particle and antiparticle. Both are an electron field. What is then the difference? Well, the time projection state to some extent. I mean, theoreticians will kill me for this kind of short corner explanations, but like, that's kind of the thing. So if you flip time in your formula, you actually move the state from particle state to antiparticle state. Okay? It's not two different particles, same particle. Which is why it is really not that special that there are particles who are their own antiparticle. Whoa, no, it just means that the symmetry is zero there.
And the charge.
So that's the point. He moved the minus sign from the energy to the quantum properties like charge. So in the end, antiparticle just means all the properties are flipped, except energy state. So mass does not change, and position either. So mass does not change sign, energy does not change sign. This was the concept. Yes?
So to put simply, the direction of the arrow is the direction of the charge, the flow of charge.
I mean, it depends, if you want. So we think of particle currents sometimes, meaning like it's a current representing the electronness of the field. And indeed, if you have, we'll go back to this slide. For example, okay, forget what is written. Imagine it's a photon that's integrating into electron and electron. You see the arrows? This is the antiparticle, this is the particle. So this is a bit special, it's W, we'll complete it a bit. So imagine this is just a photon, looks exactly the same diagram, going electron, anti-electron. What you can see there is that, of course, there is like a connected flow following the arrow. And that is the whole point. There is a flow of electronness, so to say. When the flow reverses time, we consider it, we, humans, interpret it as an antiparticle. When the flow is aligned with time, we consider it a particle. But in a sense, it's just you with flow of electrons. Okay, is that kind of answer? Good. So let's go back to the previous one.
Sorry, can I maybe ask just one quick question myself on this point?
Yeah.
Because the arrows, we already know that students, when they see the Feynman diagram, the immediate reaction is, obviously, this is the direction of movement. So
yes, it is not true.
Yeah, so it's not true, right? The arrow is really just a way how we illustrate it. What would be your opinion when we talk about Feynman diagrams in the classroom, when we want to show it to students? Would it be a valuable solution to leave the arrows out and really just name or like put the real description of each line? So let's say, okay, here's the positron, here's the electron, instead of doing the arrows, because if they're labeled, the message for the students is the same, right?
Though in textbooks, Jeff, the arrows are put in and in exams and everything. They want the arrows, even
No, but
it's more like a fundamental hypothetical question. Do you think it is educationally, does it serve a purpose educationally to have the arrows, right?
Yeah, exactly. Yeah.
Well, I mean, I think one nice feature of the arrows is that you see where there should be particles, antiparticles. It shows this kind of flow.
Yeah.
And I think, I don't know, you would have to stress indeed. I mean, it falls back to the same thing. That is, this is not representing what is happening there.
Yeah.
So it cannot be movement to begin with because it's not representing a particle going here.
Yeah.
But what? For me, the arrow is like the sign that puts the numbers 1 minus 1. Just.
You see, I mean, I take it extremely literally. For me, it's a flow. I really imagine an electron current flowing in that direction, and not current as an electric current, but an electronness. And you see, the point with this thing is language is really doing it short here. And which is why it always goes wrong when you go to quantum theory and you go to layman, because there is no adequate language to actually show the meaning of the mathematics. Which is why I stressed this so much yesterday and now again, like it is literally means this arrow comes there from electronness flow.
In time?
No, and that's the point. Because it is not a pictorial representation of space-time. It is a pictorial representation of a mathematical thing that happens. And you can have, so, which is why again, language is shorting us here because it's not a flow as a flow of water or something that is dynamic in time. No, it is a mathematical flow. And the flow is a word that is used a lot in mathematics. Flow and flux, this kind of things. So we have this kind of flows in manifolds when you go to very advanced field theories, very complex. Because these are currents, mechanics, that are conserved, and they follow from Newton's theorem. The second part of Newton's theorem, which is often not stated, is with every conserved charge, there is a conserved current. And that means that along this electronless flow, it remains the same electronness. Nothing changes there, which is a very strong statement.
Even the second part of that theory again, sorry?
Sorry?
What was the concept with conservation of charge? What was the second part of that theory you said again?
Conservation of current.
Conservation.
So there is a mathematical expression for the electron current, which is the part of the Lagrange that you see. Okay, now I need a blackboard. How does this thing work?
I think by hand.
This one?
No, sorry, this one no. There's a button. I think it's the small one on the right. But I'm just mindful, we skipped a couple of people who had their hands up.
Yes,
Dashka especially with my passion, Hugo and Janet as well. So we should maybe. And I was the one who jumped in ahead of you, so I apologize myself. That's a hardcore button.
Yes, but this, I want to remove this, it's not right. It's,
that is permanent mark.
That is permanent, yes, it's very
Don't forget it. Yeah, we have it. But it's it's not as effective. There's no whiteboard cleaning for it. Wow. Maybe you want to take this question first and I can.
Yeah, but let me finish this with markers.
But let's find the markers first before I start cleaning, because if there's no marker, there's no point in cleaning.
Yeah, I found it. Yeah, it's a permanent marker. No, whiteboard marker. Okay, so before we go to the questions, let me just try to tie this thing about current. So,
you need something clean there?
No, yesterday I was doing a thing with phi, scalar fields. Let's go directly to the electron field, which is almost the same. You just have psi and anti-psi. It does not mean particle, antiparticle, because it depends on your projection. This one is starting psi, ending psi bar. So it does not mean just that. It just means that this field has these two states and they're continuous. Anyway, so the Lagrangian for that one is actually the Dirac equation, very much related to the Dirac equation. It will be psi bar pi d slash minus m not squared psi. That's the Lagrangian for the free electron, which should be compared to pi d du minus m squared pi, which is what we had yesterday. Okay, because on the right you write this part as d mu phi, and this part as minus m squared. Okay, we can make these complex come together. Right? We like to write them as something in the middle because then it's not the same. So here this would mean psi bar I d slash psi minus m psi bar psi, both quadratic, kinetic terms, existing mass terms. Okay, so then now of course all of you are wondering what the fuck is d slash. So this is short for d slash d mu gamma mu. I take it that does not really help a lot.
No.
So d mu is just a standard derivation. Okay. And gamma mu is the gamma matrices, Dirac gamma matrices. So gamma mu is a set of matrix where, okay, now it doesn't really matter. Unique representation, and I don't know in my heart, I think, for example, gamma 0 is 0, 1, minus 1, 0, 0, 0, 0, 1, minus 1, 0. That would be the first one, so we have 4 like that. So how can you put a matrix in between? Well, because these things are operators as well, so you can learn vectors. So if you add an interaction, so this one, these combined means electron exists. If you add the interaction with a photon, it would be psi bar A slash psi. A properly constant G. Tells you how strong it is, of course, the charge of the electron. Not, I mean, that's probably not of course to you, but for me. Because these things always scale to a certain value, and that value will tell you how likely this will become. So that is your coupling constant, and for electromagnetic interaction, that's the charge. More charge, more interaction. Linear scaling. Did I lose you?
Yeah.
Absolutely, or?
Yeah.
All right, then I will leave it here, and we will try it as well. So this will be this vertex. Psi bar psi photon. A slash is just again A mu gamma mu. Photon field and is gamma mu. And then we come to the current. Current of the Dirac. So the electron current is psi bar gamma mu psi. The order is important because these are matrices, so vector, matrix, vector, so you cannot move the gamma somewhere else. A is just a number, but it's 4 numbers. But so you're gonna, this is a matrix per number, so this is a number per matrix. So it's indicates A0, the gamma 0 matrix, plus this thing, A1, the gamma 1 matrix. So in that context, A0 is just a number. Okay? So that is our current. And Noether tells us this thing is conserved because we have a decent case. This thing represents everything that an electronness would present if psi is an electron field. Because if you add here an A, it represents the electron interacting with the photon. If you add here a derivative, derivation is dynamics because it's a rate of change. It represents dynamics theory, it represents existing. If you add to this current a derivative, it represents the electron field existing.
Yeah, I cannot answer the last sentence. Why I have to add the derivative to the current here?
So
you add the current, why are you talking about adding a derivative? So the derivative is in the kinetic part.
Yes.
And okay, it's for the existence of the.
Yes.
Yeah. Why have to add the derivative to the current?
I mean, we don't add it. I'm just saying that if you can see this thing has 2 components, or it's made from 2 things. It's made from a current and from a derivative. That's the only thing I wanted to say. The fact that you have a current with a derivative means it's the existence behavior of a field.
Okay.
You add to the current another field and you get interaction. What I want to just give you the feeling about, what I want to convince about, that this thing is encoding the electronness. Going back to the whole question about the arrows. That's why this thing is this. It is the electron current. This thing is when you add an A to it. Okay? Now, it is very subtle. These things are difficult to get the correct representation in your mind. But remember that this diagram, in its length, represents the dot. In principle, not the lines to it. Because that would be kinetic terms. Okay? You with me on that one? So this thing represents the dot. So connecting the current to a field will tell you, I have a dot where all 3 meet, and the electron current there is conserved. If I add a derivative to my current, I get this. And now the line matters. Because then I say, this thing with a derivative means my electron field exists. And then from where to where, that's your derivation. From beginning to end of your rate of change. And you can do it infinitesimally, keep on doing it, and present it, tick, 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 tick. You could get a small step. You know, derivative is just delta x over delta t. You make delta as small as possible. You do that in steps, so we can just all the small steps. So that's why kinetic terms need derivatives, because it represents the rate of change of the field existing infinitesimal steps. I lost everyone?
No, I'm just wondering, do you think it's valuable to show the dot first and put the arrows in after?
I don't know. I don't think this is something you can show to high school.
No, just the pictures, like.
The pictures.
Yeah.
I mean, but you can maybe grasp them, get them a bit of feeling of electronness. If you would achieve the realization that this thing represents the dot, and the other one represents the line, and that when you make a diagram, now I will do it here, that looks like this. So, dot, dot. So which is why, by the way, I like this curved drawing. It doesn't matter, it doesn't represent position, but curved because of current, right? It's exactly the same as this. It's fine. So, you made them realize this drawing is actually consisting of a few bricks. Brick 1, dot. Brick 2, dot. Brick 3, this line, which is the kinetic terms, something like d mu, a mu. It's a bit longer, but right. Like the photon field existing. Dot would be psi bar a slash psi. And on this one, again, electron field existing. That's the elementary bricks that you glue together. And that's how we like to think of Feynman diagrams. We get components, we glue them together. There are subtleties, obviously, very important subtleties, because this thing is now a real particle. So at some point in your mental exercise, this one becomes a correction with everything included because it's now a real thing. These details are always left out, but you should be aware of it. Right? Are you with me there?
Do the arrows always point in the same direction?
So you can do whatever you want with the arrows, as long as along the line they don't contradict each other. Because then your current is not conserved. Writing something like this is heresy. I have seen people do it, physicists. And then they're like, yeah, it's the movement. Because then, of course, no wonder that people get confused. The arrow is not representing movement because the diagram is not even representing a physical thing. This thing would mean your current is not conserved because it cancels each other.
I'm getting mindful of our time available. We have about 10 more minutes left.
What?
We can maybe stretch it a little bit, but we definitely should start taking some questions. And I've seen Dashka.
Was it not 1 hour and a half?
No, 1 hour. But we can maybe, don't look at me like this. We have half an hour coffee break. I can buffer a little bit. No worries. Dashka was very, very patient for your time and chance as well, and too good for it. And then now there are more people, so I have no idea what we do. Dashka, please.
Okay, so with this explanation, I have a lot of questions, but I will stick to the first one. It was like wave pitch waves, which is also waves, and we have like time on one arrow as well. Can we maybe like use analogy with that? Like it is not the movement of the wave, like that we put on the graph, like I don't know, x and t, like time and position.
I see a point, because a wave moves, but actually particles just go up and down.
Yeah, and also it is not like it. Yeah, you just look at one particle.
I mean,
this
it's a
time
good
this
way
is
to
position.
show that it does not always represent what is happening. On the other hand, they might start believing that then particles go up and down in a Feynman diagram. I don't know.
But like for the analogy, that it is not like movement that is on the graph.
Maybe, yeah. I mean, I think one takeaway here is that look how much effort I'm investing to get you to the correct view.
Right.
So, I don't think you should aim for a correct and full understanding of what is happening. Because I will tell you, 90% of scientists are not there. People are trying Feynman diagrams, using them professionally. People here in CMS, whatever, working on the LHC, they use Feynman diagrams, and they skip the part that this is not really what is happening, and they would make the mistakes. I mean, I make mistakes when I talk because you talk fast, they would say, and that is what is happening. But then you challenge and say, of course we know that it's not. No, 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 no. This is really the first order, and you have 90% of cases this happens. I would say that's a fundamental hiccup there that most scientists believe that is what is happening. So why would we invest all our effort to make sure kids that are 15 years old that have never seen this get the correct achieve a lot if you can make them realize, you know, if it's, and it's so much more than that. If that already is something they can accept, then you achieve a lot, in my opinion.
And also every line is like with every correction, right? It's not just like the line.
Here, no. Only external lines. That's why
Yeah,
there is this
yeah.
subtlety.
The like coming in and out, or just coming out.
In and out. Yes, yes, yes. Yeah. So the moment you have something fancy, that would be like this. Let's be more fancy. You can imagine that the moment you go to fourth order corrections, you have a lot of diagrams. I think fourth order is at this moment something like 25,000 diagrams. So when people publish, I don't think actually anybody has calculated fourth order contribution. So we have LO, leading order, or leading order diagram would be this one. It's the only way to do electron-positron that is not trivial, just stay the same, right? Leading order diagram. Next to leading order, you have corrections. You have a lot of them. We can add a loop here, we can add one here, we can correct like these, etc. So that's 4, 5, 6. Next to leading order. And I think, so then they write N3 LO. I think it's completely calculated, and that's a few people, that's like 3, 4 people that spend 4 years on it. And I think some diagrams for N4 LO are typically calculated. But keep in mind, does not mean that this is something that happens. You should also be aware that never, ever will you see this. It's a very important thing. Because people are like, no, but we can prove, and this is again something a lot of scientists do wrong. Of course not, Frederick, what are you saying? We can probe. You can break in with a test particle and then see at this very moment, okay, not here, but let's say, bring this very moment to enter this diagram. First of all, no, because it's no longer the same black box. You added extra outside particles. Secondly, how did you prove it? You're just saying that now I have this diagram, which is one of the contributions to the mathematical approximation I made describing what's happening. It doesn't show that you were seeing this. So people tend to get lost in this Feynman diagram.
All right, can I make a link to this discussion? Sorry. Yeah,
Sure.
I use that, so I show a black box, and I said it's a sum, a lot of Feynman diagrams with more and more complexity, more and more vertices. So the probability that it's heading to the complete solution can be smaller. And then I go to the calculation of the magnetic moment of the electron, the G minus 2 of the electron, and you get a very nice approximation of the experimental result. So then I give back that you really need to take into account all possibilities to go to the real world.
The only problem there is that you support the belief that the Feynman diagram was something realistic. I would start by saying it is a black box. We have no clue what it is. But we have found a description that we know that approximates reality. You can say, sine wave. I have found a description that approximates reality. The parabola. Okay, my approximation is quite badly round, but you see my point. Everybody in this room will agree that x squared has nothing to do with sine x. Yet everyone's willing to accept it here. This is a very valid approximation. Don't forget the full picture. Feynman diagrams are not the science. They are not the black box. They are tools. And then you can say, yeah, but we can keep on adding orders. Sure. But what if you actually sign it? It oscillates quite fast, right? Let's say you're interested in something 20 periods away. Well, I am sorry. No matter how many orders you add at this point, you will never reproduce this. Never. At infinity, fine, yes. But you know, the point with infinity is not really realistic. So never ever, if you approximate it here, will you describe this here? And then you can say, oh, then approximate it here. Fine, but what if I care about the behavior of the function over a few periods? then the approximation is just bullshit. And that is exactly what Feynman diagrams are to the black box. They work because we look at this at one very specific thing, but they are not the black box. They work because the way we make our experiments such that this will actually test. You know when it goes to hell, our Feynman diagrams? Proton-proton physics. And this is something innovative that's cooking, you know. You have a proton, which is a bunch of quarks. You have a proton, which is a bunch of quarks. Okay, let's draw it in a way that is a bit more consistent with what people do. So, let's do just proton, whatever this is, because anyway, it's a bunch of quarks, gluons, and whatever it is. Infinite things. You know, the proton is 3 quarks. No, it sums up to the base state of 3 quarks, but it's so much more. You add a quark and another quark, it's still the same. You have 20,000 gluons, still the same. So proton is everything again. Again, something people forget. It is not equal to 3 quarks. And then for whatever reason, you succeed in getting a gluon out here, and getting a gluon out here. Let me get a very fancy diagram that I drew yesterday as well. A top loop. Top. Why? Because top is heavy, and we're looking at Higgs. And the Higgs coupling that defines our probability is the mass of the particle, because that's how it keeps the mass. So this is the most probable, because it's the heaviest particle. No. And then it goes back to a top loop, which goes to Z, which goes to the fermions. And this goes to whatever shenanigans, the protons are kaput. Great, right? Sure. And now, completely gone. This is not possible. Happens all the time. So what do we do when we do proton-proton physics? It's only this part. And then, we know where it works. We just select data based on we know where it works. Luckily for us, when you have what we call hard physics, hard transversal, something else, it is dominated by this kind of processes. Soft physics, where you care about what happens with these protons, and they start making a whole bunch of particles, and it's all these kind of things, and it just doesn't work. We don't have a description for that. We have to do it hydrodynamically, by making functions on the spot that we measure that represent probabilities, etc. Then all Feynman diagrams are completely gone. So saying a black box is just an infinite sum of Feynman diagrams and we take some is very indigenous. It's whatever. Because that's the same as saying, in the end, if I keep adding enough polynomials, in the end I got my science. If you care from 0 to 5,
Can we take Jen's question and then Hugo, and then we will see how we wrap things up here.
I always try to think about how this could be brought to my students. So, in the past I've said, okay, things go outside are observable, and there's the uncertainty magic in the middle, and then there are these conservation laws. How can I get this idea, I think, of the flow into that without messing up the idea of the observables? I think that's my sticking point with students.
So if you are willing to get your students into a state of acceptance that there is what happens at a microscopic, idealized level where fields are separable into field interaction, etc., which is an ideal thing that is only valid in very, very, very short time. Because you can imagine if you zoom to infinity, then yes, nothing happened yet at this point. It's an assumption, and I'm not even sure if it's valid, but it feels a bit intuitive, right? If you can get into an acceptance that these things are what happens when you zoom to the infinite, so there is no time for anything else to happen, bracket. And then there is the real world, where we see the realistic things. But we have no clue of how to combine those two. If you can get them in that state, then you can start telling a lot about this microscopic state, about the Feynman diagrams, etc. Because this works under assumption, separability, that you can actually say, yes, there is a very short time unit where nothing happens. I don't think there is. Because I think the time unit is smaller than the Planck scale. And then you get into quantum uncertainty anyway, and everything happens anyway. So for this reason, I have a feeling that there is not, but I would say it's a valid enough approximation to get them to some feeling there. But these are what is representing at the absolute elementary smallest units. You have building bricks as a Feynman diagrams. But then it really goes to hell quickly because it doesn't really sum nicely because of this. And then we know, in the end, we have the full picture in one go. And everything we ever see, everything we ever observe is always the full pictures, which is what makes our life so difficult. Let's say the realization from renormalization back then that a free electron is not what we observe was a very profound realization. Very normal for us now because the whole theory is built on it, etc. But the realization that theory doesn't work because we are making the wrong connections. We're calling the free one the one we see, but of course it's not free, not true. We see the fully corrected one, and we never see the free one. So this kind of realizations, if you can get them in that state, they are further than most scientists. And then you can start talking about these things like, you see, if we now go into the realm of here we have mathematics rules, Feynman diagrams, etc., this flow is always conserved. And then you can, and then it's easier to accept. Would be my approach, but it depends on how much time you have, of course, to you see that 2 hours is not enough.
Yes, I wanted to go back to your question of how do you represent Feynman diagrams for high school students. In my case, I don't have to do Feynman diagrams. If I will ever do it, I'll just show them this is how scientists do complicated things, and this is just a model to represent really complicated equations, and the drawings look cool, so just motivation. And sometimes I think just showing them what it's done to me is enough. What I was wondering on your question that maybe if we make explicit that times goes down, that like this is a graph that in this direction represents time. I don't know if that will help the idea that that is not particles going in those directions yet, but just represent the flow of time. I'm not sure about the other direction, if writing space-time there, just being explicit about
I think it's a bit what I said before. There's no way you will get it. Let's face it. So the question is not like, how can we tell this in a way that there are no misconceptions? There will be misconceptions. You have misconceptions. I still have misconceptions. Let go of the idea that you can give a perfect picture. There is only one perfect picture, it's math. Right? And we're still fighting daily with the math. So then translating math to something that is intuitive, already a lot of scientists fail with this kind of explanations they give to what is written. Then you realize they know the math, they don't make mistakes in math, but they fumble when they have to make this into something that it means. Giving meaning is extremely difficult. So let's not expect that we can give this to kids, especially because they're not even, necessarily physics interested, so to say. So what I'm stressing yesterday and today is not what I want you to stress your kid necessarily. This is up to you, right? I mean, it's up to you what you think you can give them. But what my goal was to give you at least a few hints closer to what I believe is a more correct meaning of these things. And how you translate it, it will be very individual and it will be very different between all your classes. And in my opinion, all of them will be very fine. Because they will end up with a very wrong interpretation. Some of them will still believe, even if you say it 20 times, that this means it goes from here to there.
But I think
so what? At least you made them motivated.
Just your word choice, like you said, it's just acknowledging that exact same and doing the best you can to put that model forward with its limitations.
Yeah, but and then finally they have it wrong. At least they're motivated, interested, and they have this. Oh, this is cool. And then maybe in 10 years they cross me and I will tell them who told you this bullshit. I mean, that's life, right?
But maybe just to add on that, just one quick information. So one of my my PhD students who recently defended, and successfully, he's a doctor now, his research was really done on what do students do with Feynman diagrams. And what he did was really fancy research. He used eye tracking, so students sat in front of a laptop and had their eyes tracked to see where they look at if you show them a Feynman diagram. So he could really, through his research, first of all show what we now all agreed when we just said that it's very, 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 very likely that every student, no matter what you do, will see that as a particle going from A to B. It's something that also at CERN happens. And then, of course, the next question is, okay, as you just said, can we still motivate them? Because Feynman diagrams are pop culture, right? You see them if you are scientifically aware. So you want to do something with it. But the question is, as an educator, and this is something that you will have to decide, do you want to focus on the meaning of the Feynman diagrams and the math behind it? Or do you maybe want to use them as a context, so not focusing on the content, but as a context to illustrate one of the key essentials in physics, which is conservation laws. Because in every Feynman diagram, conservation is there. And so even if you only on a very low level give students a Feynman diagram, where you label everything except for one thing, for example, you give them the charges, students with no knowledge will be able to tell you what is the electric charge of this particle, in this case, or the weak charge, or whatever. And it's a nice trick, it's a treasure hunt for them, right? I'm not saying that through doing this you will teach Feynman diagrams, or maybe even interaction laws, or whatever, but at least you sneak it in and you can use it in your classroom. So this is just one more point.
Yeah.
No, precious time for you.
I think if you can get them to the idea, which is something they might actually get, that it's actually black box. And actually nobody knows what happens. And things like, whenever somebody presents this is a Higgs event, no, it's a lie. You don't know. There is a 0.1% chance that this was a Higgs, but you know because you don't see it. It's a black box. This in, this out, and Higgs is one of the constituents of this probability. And as I said, scientists make mistakes all the time. They teach it to high schoolers. My professor, look, and this is Higgs event. It's a bit of pity. I mean, fine. He doesn't want to go into details, but I think it's something actually you can teach them. It's no, we don't know. It's a black box. And we have ideas on how to describe the black box, and then you can spend some time on Feynman diagrams to give them power, and then I don't know what you want to do. The concept of we don't know, it's a black box, is something I think you can implement.
Alright. I see we have many, many more questions. What I would like to do now is, seeing that especially also today the lunch break is relatively short and everything could, move left and right. And we are now 10 minutes behind schedule. That we thank Frederick first of all very, very much. I'm happy because honestly, when I discussed with Frederick a few weeks ago, a month ago, I told him exactly this is my ideal scenario. I want the first session to be chaotic, or at least, overwhelming to an extent, but then bringing it back in the second. And I feel like now with the second one, we all get a better way of looking at it. For those of you who still want to discuss with Frederick, I'm pretty sure we can still stay around 2 more minutes, unless this is not the case.
No, because I thought it was until 11.
There we go. But we will start again at 11. We will start again at 11. Yeah, the time is always moving this direction. You can leave stuff here for everyone who still wants to discuss. Grab Frederick when he's still around. And yes, you take a good picture because today we do a good picture. So everyone of course, this morning. Very nice, yes. These very awesome.
Yeah. Do you want to go get someone?
No,
for the picture?
Again, I just would.
Is there any
Thank you, Jen. There we go, yeah.
Okay, we'll go for easy explanation.
Yeah.
I want to learn about Feynman diagrams and understand what they are doing.
Oh, nice. Oh, this is awesome. All right. So, everyone who is now confused on a higher level, say cheese. Cheese. Can I say cheese backwards? Cheese backwards.
She's backwards.
This joke will never not be funny. I'm sorry. Look at that. Oh, look at how you smile. And now I'm sure we take one where you don't do anything. We get a proper grouping. I love it. Very good.
Thank you. Oh man.
Which would be awesome.
Totally. Alright, we want to No, that's okay. Yeah. 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 Yeah.